Let's talk about frequency so we can have a better understanding of alternating current. If we were measuring a DC voltage supply in a circuit with a load and a power switch with an oscilloscope, we would see its frequency waveform. If I turn the switch on to allow current to start flowing for 30 seconds, then turned it back off for 30 seconds, then turned it back on, and continued doing this every 30 seconds, the frequency is 1 cycle per minute. If I could switch it on and off every second, then that would be 1 cycle per second, or 1 hertz. So understand that you are measuring a time frame and the peak and decline of the voltage in that time frame. In DC, it's a quick to peak and quick to zero change. In alternating current, because the magnet is getting near, we see an increase in moving electrons, centering where we see the highest number of electrons moving and giving us a peak voltage, and then moving away, we tend to see the waveform decline. Again, we still reach a peak voltage just like we did in DC, but the change is a slower incline and decline. In alternating current, we're counting both the north and south poles passing as 1 cycle. In the United States, this alternation happens 60 times a second. In Europe and other countries, it's 50 times a second. This frequency is expressed in hertz. You can get an alternating current waveform from DC voltage as well, with some circuitry help that we will discuss later when we talk about DC motors. DC current only has a large magnetic field during its incline, then stabilizes. Alternating current is in a constant movement of incline and decline, creating a large pulsating magnetic field. It's this constant magnetic field we need to do the work, and why AC is the chosen source for electric power. Back at the power generation plant, large turbines are being powered by something: water, air, natural gas, coal, something that turns large generators. I'm going to simplify my description. You have a generator using a north-south pole magnet. Let's talk about one phase or single phase. As the north magnet nears the coil, current starts to flow. It centers up with a peak voltage. As it pulls away, current starts to slow. The south pole comes around and current starts to flow in the opposite direction. If we measure from one side of the coil to the other, we would measure a difference of 120 volts AC. Again, I am simplifying the voltage. If we added 2 more coils, then we would have 3-phase. And again, to simplify, let's say each phase creates a voltage difference of 120 volts AC to ground or neutral. 3-phase is created because the magnets are passing the coils at different times, creating peaking waveforms or peaking voltages at different intervals. This is what out of phase means. These lines being out of phase by 120 degrees cause the voltage difference of potential to be higher than if we just measured to ground, giving us 240 volt or 208 voltage ranges. All power generation is 3-phase. The 208-240 comes from the transformers used to reduce power to delta or star. I will not be covering delta and star or Y power supplies. However, I recommend you familiarize yourself with their characteristics. Star or Y transformers are what is popular today to bring power into your house or business. You will find 3-phase distribution almost everywhere except out in country rural areas. The voltage levels discussed were drastically understated for some basic understanding. Let's go outside and look at the power lines. The power generation plant generates voltage at around 16,000 volts, then use a step-up transformer to boost the voltage to somewhere from 44,000 to 765,000 volts for transmission at lower amperages. Before we go any further, let's briefly discuss the magic of the magnetic field we discussed earlier and make an introduction into transformers. Transformers use a primary winding with an input AC voltage and a secondary, which is an output voltage. Transformers can be step up or step down. The voltage from one side never touches the voltage on the other. On the primary side, as current flows through the windings, it creates a magnetic field. This magnetic field induces a current in the windings on the secondary side. We will discuss transformers in depth later. Just wanted to point out that the electricity that gets to where we use it goes through a series of electrical magnetic fields reacting on one another. So the electricity being created at the power plant never actually reaches us, only the reaction of it. I will discuss transformers later in detail. A transmission line is the big towers you see. Note that the wires are in sets of 3. As it goes to substations, the substation steps it down to go out for local distribution. Local distribution steps it down using a step-down transformer. In most areas, they also supply a grounded neutral. I will discuss it further when we get into breaker panels. If you look at most electric poles running along the street, you will see 3 wires on top. That's the 3-phase coming from your local substation to you. Typically, the voltage on the 3 uninsulated wires could be 6,000 to 12,000 volts, but it really varies from area to area. The voltage is stepped down again using a transformer to go to each business or household. If you have ever looked at your electric bill charges, there's one line that says distribution. This pays for the wires, poles, and transformers used to bring power to you. The charge is based on your kWh, your kilowatt per hour use that you were billed for on a separate line. Large factories and industrial buildings can save money by using their own transformers to step down voltage, so it's not unlikely to see higher voltages like 480 or 600 volts in some large buildings. Using the magic magnetic field we discussed earlier, for typical business use, the voltage is stepped down to 120, 208, or 240 volts single or 3-phase, and residential would be 120, 208, 240 single phase. The 208, 240 is all based on how the transformer steps down the voltage. Typically today, it's 208 volts. Additionally, the voltages could vary depending on where you live in relation to the substation. The farther away, the voltages will likely be lower. We will take a look at the breaker panel to see how we use this delivery.